Time flows like a gentle river, carrying us from moment to moment, breath to breath. But what if that river could bend? What if we could step outside its current, watch it curve and loop back on itself? Tonight, we'll drift through the elegant mathematics and mind-bending possibilities of time travel, where Einstein's equations whisper secrets about the nature of reality itself. Hi, I'm Luna, and if you love falling asleep to curious science, quiet wonder, and starry night stories, you're in the right place. So grab your coziest blanket, get comfy, and don't forget to hit like and subscribe because tonight, we're embarking on a gentle journey through the physics of time travel, where the boundaries between science and dreams blur like starlight through a telescope, and where each discovery brings us closer to understanding the deepest mysteries of our universe. Let's begin our journey by floating gently down the river of time as we understand it. For most of human history, time seemed as fixed and unchanging as the mountains, a steady, universal heartbeat that marked the same rhythm for everyone, everywhere. A second was a second, whether you were sitting quietly by a fireside or racing across the countryside. An hour passed at the same rate for a farmer tending crops and a sailor crossing distant seas. This intuitive understanding of time served humanity well for thousands of years. We built calendars around it, planned our lives by it, and organized entire civilizations according to its steady rhythm. Time was the great constant, the one thing we could depend on in an uncertain world. It moved forward, always forward, carrying us from birth to death in an unbroken line. But late in the 19th century, scientists began to notice something peculiar about light. No matter how fast you were moving when you measured it, light always traveled at the same speed, about 186,282 miles per second. This seemed impossible. If you're driving toward an oncoming car, that car appears to approach you faster than it would if you were standing still. If you're running away from someone throwing a ball, the ball reaches you more slowly than if you were running toward it. Yet light behaved differently. Whether you were racing toward a star or drifting away from it, the light from that star always reached you at exactly the same speed. This strange behavior of light troubled physicists like a gentle riddle whispered in their dreams. The mathematics of the time couldn't explain it. The very foundations of physics seemed to shiver under the weight of this impossible consistency. It was as if the universe was trying to tell them something profound about the nature of reality itself, but they didn't yet know how to listen. Then, in 1905, a young patent clerk in Switzerland named Albert Einstein had a moment of profound insight that would forever change our understanding of time, space, and the very fabric of reality. Einstein realized that if the speed of light was truly constant for all observers, then something else had to give. And that something was time itself. Einstein's special theory of relativity revealed that time is not the universal constant we had always believed it to be. Instead, time is relative. It flows differently depending on how fast you're moving through space. The faster you travel, the slower time passes for you relative to someone standing still. This isn't just a theoretical curiosity. It's a fundamental property of our universe, as real and measurable as the warmth of sunlight on your skin. Imagine two twins, one who stays on Earth and another who embarks on a journey to a distant star at nearly the speed of light. To the traveling twin, the journey might feel like it takes just a few years. But when they return to Earth, they would find that decades had passed for their earthbound sibling. The traveling twin would have journeyed into the future, aging more slowly than everyone they left behind. This phenomenon, known as time dilation, isn't science fiction, it's science fact. We see it in the behavior of particles in accelerators. We account for it in the GPS satellites that help us navigate. And we measure it in atomic clocks flown on airplanes. Time truly does flow at different rates, depending on motion and gravity, like a river that runs faster in some places and slower in others. But Einstein's insights went even deeper. In 1915, he expanded his theory with general relativity, which revealed that massive objects actually bend the fabric of spacetime itself. Picture a stretched rubber sheet with a heavy bowling ball placed in the center. The ball creates a depression, and if you roll a marble nearby, it will curve around the depression rather than traveling in a straight line. Similarly, massive objects like stars and planets create curves in spacetime, and these curves are what we experience as gravity. Near massive objects, time itself slows down. A clock sitting on the surface of the sun would tick more slowly than an identical clock floating in empty space. The stronger the gravitational field, the more time slows. This gravitational time dilation means that time passes more slowly at sea level than it does on a mountaintop. Though the difference is so small we never notice it in our daily lives. These discoveries opened the door to our first real glimpse of time travel. If you could somehow find yourself near an extremely massive object, perhaps orbiting close to a black hole, time would pass much more slowly for you than for observers far away. You could experience hours while years passed in the outside universe. When you finally returned to less gravitationally intense regions, you would have traveled into the future. This form of time travel, forward time travel through time dilation, is not only theoretically possible, but practically inevitable for anyone moving at high speeds or living in strong gravitational fields. Astronauts on the International Space Station actually experience time slightly differently than we do on Earth's surface, though the effect is measured in microseconds over months of orbit. The realization that time is malleable, that it can stretch and compress like taffy pulled by invisible hands, transformed our understanding of the universe. We began to see that space and time are not separate entities, but are woven together into a single fabric, space-time, that can be curved, twisted, and potentially manipulated in ways that our ancestors never dreamed possible. As we drift deeper into this exploration, let's allow ourselves to feel the profound beauty of these discoveries. Einstein's equations revealed that we live in a universe far stranger and more wonderful than anyone had imagined. Time, that most fundamental aspect of our existence, turns out to be as flexible as the melody of a lullaby, changing its rhythm based on the cosmic dance of matter and energy around us. In the heart of our galaxy, about 26,000 light-years from Earth, something extraordinary lurks in the darkness. It's called Sagittarius A, and it's a supermassive black hole containing the mass of about 4 million suns, compressed into a region smaller than our solar system. Around this cosmic giant, stars dance in elliptical orbits that bring them dizzyingly close to the edge of something that defies our everyday understanding of reality: the event horizon. Black holes represent perhaps the most extreme environments for time travel that nature has to offer. They are places where Einstein's predictions about the behavior of spacetime are pushed to their absolute limits, creating conditions so extraordinary that time itself behaves in ways that seem almost magical. To understand how black holes might serve as gateways through time, we need to gently explore what happens as we approach these cosmic giants. Imagine you're drifting slowly toward a black hole in a spacecraft, watching the stars wheel overhead. At first, nothing seems unusual. Space looks much the same as it does anywhere else: vast, dark, and filled with distant points of light. But as you draw closer, subtle changes begin to manifest. The gravitational field grows stronger, and according to Einstein's general relativity, time begins to slow down relative to observers far away from the black hole. If you had a friend watching you from a safe distance, they would see your spacecraft appearing to slow down as you approached the black hole. Your movements would become increasingly sluggish from their perspective. Your radio signals would arrive with longer and longer delays, and the light from your spacecraft would gradually shift toward the red end of the spectrum as gravitational redshift takes hold. To your distant friend, it would appear as if you were frozen in time at the event horizon, never quite crossing that mysterious boundary. But from your perspective inside the spacecraft, something entirely different would be happening. You wouldn't feel yourself slowing down at all. Your watch would tick at its normal rate, your thoughts would flow at their usual pace, and time would seem to pass normally. This is one of the most beautiful and mind-bending aspects of relativity. Time dilation is always relative. You don't feel your own time slowing down. You only notice the difference when comparing your experience to that of observers in different gravitational fields. As you crossed the event horizon, you would have effectively traveled into the future of the outside universe. While only hours or days might have passed for you during your journey to the black hole, years, decades, or even centuries could have elapsed in the wider universe. When or if you somehow emerged from the black hole's influence, you would find yourself in a future Earth, having skipped forward through time like a stone skipping across the surface of a pond. But black holes offer possibilities for time travel that go beyond simple time dilation. Some of the most exotic solutions to Einstein's equations suggest that certain types of black holes, rotating black holes called Kerr black holes, might contain structures that could theoretically allow for even stranger journeys through time. Inside a rotating black hole, the intense gravitational field doesn't just curve spacetime. It drags spacetime along with the black hole's rotation in a phenomenon called frame dragging. This creates a region called the ergosphere, where spacetime itself is being pulled around so violently that anything within it is forced to rotate with the black hole, whether it wants to or not. Deep within such a black hole, theoretical physicists have identified regions where the normal structure of spacetime might break down entirely. These regions, called closed time-like curves, represent paths through spacetime that loop back on themselves. A traveler following such a path might theoretically arrive at their starting point not just in space, but in time as well, effectively traveling into their own past. The mathematics of these solutions is elegant and consistent with Einstein's equations, but they exist in realms so extreme that we can barely imagine what they might be like. Near the singularity at a black hole center, where matter is compressed to infinite density and spacetime curvature becomes infinite, the normal rules of physics, as we understand them, begin to break down. It's possible that quantum effects, which become important at the smallest scales, might prevent such extreme time travel scenarios from actually occurring. Another fascinating possibility involving black holes is the theoretical existence of wormholes, hypothetical structures that could connect distant regions of spacetime through shortcuts that bypass the normal three-dimensional space we experience. If such wormholes exist, they might serve as tunnels not just through space, but through time as well. Picture spacetime as a vast sheet of paper. Normally, to travel from one point to another on the paper, you would have to move across the surface, following the curvature created by massive objects. But a wormhole would be like folding the paper so that two distant points touch, then poking a hole through both layers. A traveler could potentially pass through this hole and emerge at a distant location, and possibly at a different time, almost instantaneously. The mathematics of wormholes was first explored in detail by Einstein and his colleague Nathan Rosen in 1935, leading to these structures being called Einstein-Rosen bridges. Later work by physicists like Kip Thorne showed that, in principle, wormholes could be manipulated to create time machines. If you could somehow move one end of a wormhole at high speed, while keeping the other end stationary. Time dilation would cause the two ends to experience time at different rates. Eventually, the moving end would become synchronized with an earlier time at the stationary end, creating a pathway into the past. However, keeping a wormhole open would likely require exotic matter with negative energy density, a substance that we've never observed and that might not exist in nature. The energy requirements would be enormous, possibly requiring the manipulation of matter and energy on cosmic scales. Even then, quantum effects might prevent the formation of stable wormholes suitable for time travel. Despite these challenges, the study of black holes continues to reveal new possibilities for understanding the nature of time. Recent discoveries, such as the first direct images of black holes captured by the Event Horizon Telescope, have confirmed many of Einstein's predictions about how these objects behave. Each observation brings us closer to understanding whether the extreme time travel scenarios predicted by general relativity could actually occur in nature. As we contemplate these cosmic giants and their relationship to time, we're reminded of how much mystery still surrounds us. Black holes exist at the intersection of the very large and the very small, where general relativity meets quantum mechanics in ways we don't yet fully understand. They represent natural laboratories where the universe tests the limits of physics, creating conditions so extreme that they stretch our theories to their breaking points. In the quiet darkness around a black hole, where time moves like honey and space bends beyond recognition, we find some of the universe's most profound lessons about the nature of reality. These cosmic monuments to gravitational extremes remind us that time, the steady companion of our daily lives, is far more flexible and mysterious than we ever imagined. Deep within the atom, in a realm smaller than anything we can directly perceive, a strange and beautiful dance unfolds. Here, in the quantum world, the familiar rules of classical physics dissolve into probability and uncertainty, and particles behave in ways that challenge our most basic assumptions about reality. It's a realm where a single particle can exist in multiple places simultaneously, where the act of observation changes the nature of what we observe, and where the very concept of time might work differently than we understand it in our everyday experience. Quantum mechanics, the theory that describes this microscopic realm, has revealed phenomena so counterintuitive that they seem to belong more to the world of dreams than to rigorous science. Yet these quantum effects are not just theoretical curiosities. They underlie the operation of lasers, computer chips, MRI machines, and countless other technologies that shape our modern world. And some physicists believe that quantum mechanics might hold the keys to understanding time travel in ways that go beyond Einstein's relativity. One of the most fascinating aspects of quantum mechanics is the principle of superposition. In our everyday world, an object is either here or there, moving or stationary, spinning clockwise or counterclockwise. But quantum particles can exist in combinations of these states, simultaneously exploring multiple possibilities until the moment they interact with something that forces them to choose a definite state. Imagine a quantum coin that, instead of landing heads or tails, exists in a ghostly combination of both until someone looks at it. This isn't just a limitation of our knowledge, it's a fundamental property of quantum systems. The particle literally exists in multiple states at once, exploring all possible paths through reality like a dreamer, experiencing all possible dreams simultaneously. This quantum superposition extends to time as well as space. Some interpretations of quantum mechanics suggest that particles can exist in superpositions of different temporal states, effectively experiencing multiple timelines simultaneously. A quantum particle might, in some sense, exist at different moments in time all at once, exploring past, present, and future, until some interaction collapses this temporal superposition into a single, definite moment. Another quantum phenomenon that hints at strange relationships with time is quantum entanglement. When two particles become entangled, they form a connection that persists regardless of the distance separating them. Measuring one particle instantly affects the state of its entangled partner, even if that partner is on the other side of the galaxy. Einstein famously called this spooky action at a distance, and it troubled him because it seemed to violate the principle that nothing can travel faster than light. What makes entanglement even more mysterious is that this instantaneous connection appears to transcend time as well as space. Some experiments have suggested that particles can become entangled across time, with measurements performed on a particle in the present affecting the state of a particle in the past or future. These temporal correlations hint at a universe where the boundaries between past, present, and future are not as absolute as we might think. The quantum world also introduces us to the concept of virtual particles, fleeting entities that pop into existence out of the vacuum of empty space, exist for impossibly brief moments, and then disappear back into nothingness. These virtual particles are not just mathematical conveniences, they have measurable effects on the physical world. They contribute to the slight shift in energy levels of atoms. They create a tiny force between parallel conducting plates, and they might even play a role in the expansion of the universe itself. Virtual particles seem to violate our intuitive understanding of causality and time. They can borrow energy from the future, exist for a brief moment, and then pay that energy back before their debt to the universe's energy budget is noticed. This process, allowed by Heisenberg's uncertainty principle, suggests that the quantum vacuum is not empty at all, but rather a seething foam of potential particles constantly appearing and disappearing in a cosmic dance of creation and annihilation. Some physicists have speculated that these quantum fluctuations of the vacuum might be related to the nature of time itself. Perhaps time is not the smooth, continuous flow we experience at large scales, but rather emerges from the collective behavior of countless quantum events occurring at the smallest possible scales, the Planck scale, where distances are measured in units, about 10⁻35 meters, and time intervals in units of about 10⁻43 seconds. At this unimaginably small scale, spacetime itself might be foamy and discontinuous, with virtual particles and quantum fluctuations creating a bubbling landscape of microscopic wormholes and time loops. Some theories suggest that this quantum foam might provide natural mechanisms for time travel, allowing information or even matter to slip through these microscopic spacetime shortcuts and emerge at different moments in time. The many worlds interpretation of quantum mechanics offers another perspective on time and causality that relates to time travel. According to this interpretation, every quantum measurement splits the universe into multiple parallel realities, each corresponding to a different possible outcome. In one world, the quantum coin lands heads. In another, it lands tails. Both outcomes are equally real, existing in parallel universes that branch off from each moment of quantum decision. If the many worlds interpretation is correct, then time travel might not involve moving backward along a single timeline, but rather moving between parallel timelines that correspond to different possible histories. A time traveler might not be able to change their own past, but they could potentially visit alternate versions of history where different choices were made and different events unfolded. This perspective on time travel helps address some of the paradoxes that have long troubled physicists and philosophers. If you traveled back in time and prevented your own parents from meeting, you wouldn't create a paradox. You would simply move to a parallel timeline where you were never born, while your original timeline remains unchanged. The universe splits to accommodate all possibilities, ensuring that consistency is maintained across the multiverse as a whole. Quantum mechanics also introduces the possibility of closed time-like curves at the quantum level, paths through spacetime that loop back on themselves, allowing particles to interact with their own past states. Unlike the macroscopic closed time-like curves that might exist near black holes, quantum closed time-like curves could potentially exist at the microscopic level, mediated by quantum fluctuations and virtual particles. Recent theoretical work has explored how quantum systems might behave in the presence of closed time-like curves. Some researchers have found that quantum mechanics naturally prevents many of the paradoxes that would arise from classical time travel. The probabilistic nature of quantum mechanics seems to smooth out potential inconsistencies, allowing quantum information to flow backward in time while maintaining overall coherence. One particularly intriguing quantum effect related to time is quantum tunneling. In the quantum world, particles can pass through barriers that should be impossible to cross according to classical physics. A particle encountering an energy barrier doesn't necessarily bounce off or stop. It has a certain probability of appearing on the other side of the barrier, as if it had tunneled through solid matter. Some experiments have suggested that quantum tunneling might occur faster than light, or even instantaneously. If this is true, it raises fascinating questions about the relationship between quantum mechanics and special relativity. Does the tunneling particle experience time differently during its passage through the barrier? Could quantum tunneling provide a mechanism for sending information backward in time? The questions raised by quantum mechanics about the nature of time are still largely unanswered. We have mathematical frameworks that describe quantum behavior with incredible precision, but we still don't fully understand what these mathematics tell us about the fundamental nature of reality. The quantum world remains mysterious, a realm where our classical intuitions about time, space, and causality break down and are replaced by probability, uncertainty, and interconnectedness. As we contemplate these quantum mysteries, we're reminded that time itself might be far stranger than we ever imagined. Perhaps time is not a river flowing from past to future, but rather an ocean where all moments exist simultaneously, connected by quantum correlations that transcend our ordinary understanding of sequence and causality. In the quantum realm, the future might influence the past just as much as the past influences the future, and the very act of consciousness might play a fundamental role in determining which possibilities become real. Among all the puzzles that time travel presents to our understanding, none are more captivating or perplexing than the paradoxes that seem to arise when we imagine journeying backward through time. These paradoxes have entertained philosophers, physicists, and storytellers for generations, weaving themselves into our collective imagination like riddles whispered by time itself. Yet as we examine them more closely, these paradoxes reveal profound truths about the nature of causality, free will, and the logical structure of reality. The most famous of these puzzles is the grandfather paradox, a thought experiment that captures the fundamental challenge of backward time travel. Imagine you possess a time machine and decide to travel back to a time before your grandparents met. If you were to prevent their meeting, perhaps by convincing your grandfather to move to a different city, then your parents would never be born, and consequently, neither would you. But if you were never born, who traveled back in time to prevent your grandparents from meeting in the first place? This paradox creates what logicians call a causal loop, a circular chain of cause and effect that has no clear beginning or end. Your non-existence prevents your birth, which prevents your time travel, which prevents your interference, which allows your grandparents to meet, which leads to your birth, which enables your time travel, and so on in an endless cycle of logical contradiction. At first glance, such paradoxes seem to provide strong evidence against the possibility of backward time travel. If traveling to the past necessarily creates logical impossibilities, then perhaps nature simply forbids such journeys. This line of reasoning has led some physicists to propose what Stephen Hawking called the chronology protection conjecture. The idea that the laws of physics somehow prevent the formation of closed time-like curves that would allow backward time travel. But as physicists have studied these paradoxes more carefully, they've discovered that the situation is more nuanced than it first appears. The grandfather paradox assumes that time travelers have unlimited freedom to change the past. But what if the universe has mechanisms that prevent such changes? What if the past, once established, possesses a kind of logical resilience that resists alteration? One possible resolution is the idea of self-consistent timelines. In this scenario, any time travel that occurs must be consistent with the history that has already unfolded. If you travel back in time, you don't create a new timeline. You fulfill the timeline that was always meant to be. Your actions in the past were always part of history. They just happen to be actions performed by a time traveler from the future. Consider a different example. Suppose you travel back in time and encounter your younger self. Common sense might suggest that this meeting would change your memories of your youth. Surely, you would remember meeting a time traveler. But in a self-consistent timeline, you already do remember this meeting. The older version of yourself that travels back in time is the same person that your younger self remembers meeting. The loop is closed, consistent, and paradox-free. This principle of self-consistency might apply to more dramatic changes as well. Perhaps you can't prevent your grandparents from meeting, because every attempt you make to interfere will somehow fail or backfire. Maybe your interference actually causes them to meet in the first place. The universe, in this view, has a kind of logical immune system that preserves consistency by ensuring that effects always align with their causes, even when those causes come from the future. Some physicists have explored this idea mathematically, studying whether solutions to Einstein's equations that allow closed time-like curves can remain self-consistent. They've found that in many cases, the constraints of consistency severely limit what a time traveler can do. The time traveler becomes an actor in a predetermined script, able to move freely within their role, but unable to change the fundamental plot of history. Another approach to resolving time travel paradoxes comes from quantum mechanics. As we explored earlier, quantum systems exist in superpositions of multiple states until they interact with something that forces them to choose a definite state. Some physicists have suggested that quantum superposition might apply to time travel scenarios as well. In this quantum approach, a time traveler attempting to change the past would create a superposition of different possible histories. The universe would explore all possible outcomes simultaneously, timelines where the grandfather paradox occurs, timelines where it doesn't, and everything in between. The final, observed history would emerge from this quantum superposition according to the probabilistic rules of quantum mechanics, naturally selecting outcomes that avoid logical contradictions. This quantum resolution suggests that time travel might work differently at the microscopic and macroscopic levels. Individual particles or bits of quantum information might be able to travel backward in time relatively freely, creating temporary inconsistencies that are resolved through quantum decoherence. But larger objects, like human time travelers, would be subject to stronger consistency constraints that prevent major paradoxes from occurring. The many worlds interpretation of quantum mechanics offers yet another perspective on time travel paradoxes. If every possible outcome of every quantum event creates a new parallel universe, then time travel might involve moving between these parallel timelines, rather than altering a single, fixed history. A time traveler preventing their grandparents from meeting wouldn't create a paradox. They would simply move to a parallel universe where they were never born, while their original timeline remains unchanged. This multiverse approach to time travel eliminates paradoxes by allowing all possibilities to coexist in separate realities. Every choice the time traveler makes creates new branch points in the quantum multiverse, generating countless parallel histories that accommodate every possible outcome. The time traveler becomes an explorer of possibility space, visiting alternate versions of history rather than changing the fundamental nature of their own past. Some philosophers have questioned whether these proposed resolutions truly solve the paradoxes or merely relocate them. The principle of self-consistency, for example, seems to require a form of backward causation, where future events influence past events in ways that preserve logical coherence. This raises questions about free will and determinism. If the future influences the past, do we truly have the freedom to make different choices? Or are our decisions constrained by the need to maintain consistency with future events? The quantum and many worlds approaches raise their own philosophical puzzles. If quantum mechanics resolves paradoxes by exploring all possibilities simultaneously, what determines which possibility we ultimately observe? And if the many worlds interpretation is correct, does traveling to a parallel timeline really constitute time travel in any meaningful sense? Or is it simply travel between different possible worlds? These questions touch on some of the deepest issues in philosophy and physics. The nature of time, the reality of free will, the relationship between possibility and actuality, and the role of consciousness in determining what we experience as real. Time travel paradoxes force us to confront these fundamental questions in ways that pure theory alone cannot. Perhaps the most beautiful aspect of these paradoxes is not their potential resolution, but their ability to illuminate the intricate logical structure of reality. They reveal that time, causality, and existence are interconnected in ways that challenge our most basic assumptions about how the universe works. Each proposed solution opens new avenues of inquiry and reveals new depths of mystery. As we drift through these conceptual landscapes, we might find comfort in the possibility that the paradoxes of time travel, like koans in Zen Buddhism, are not meant to be solved in any conventional sense. Instead, they serve as doorways to deeper understanding, inviting us to release our attachment to linear thinking and embrace the beautiful complexity of a universe where past, present, and future dance together in patterns too intricate for any single mind to fully comprehend. In contemplating these paradoxes, we're not just thinking about time travel, we're exploring the very foundations of logic, causality, and existence. We're asking what it means for something to be real, what it means for events to be connected, and what it means for time to flow. These are questions that connect us to the deepest mysteries of consciousness and cosmos, reminding us that even our most abstract intellectual pursuits ultimately lead us back to wonder at the magnificent puzzle of existence itself. In the vastness of space, where galaxies spiral through the cosmic dark like slowly turning pinwheels of light, the fabric of spacetime stretches smooth and nearly flat. But here and there, massive objects create ripples and curves in this fabric, like stones dropped into a still pond or heavy sleepers shifting in a cosmic bed. These natural distortions in spacetime give us gravity, guide the paths of planets and stars, and create the time dilation effects that make natural time travel possible. But what if we could do more than simply observe these cosmic phenomena? What if we could engineer spacetime itself, reshaping the very fabric of reality to create our own pathways through time? This is the realm of spacetime engineering, a field that exists at the intersection of theoretical physics and science fiction, where the tools of tomorrow might allow us to build bridges across time just as surely as we build bridges across rivers today. The mathematics that describe these possibilities are as elegant as they are exotic, revealing potential futures where humanity might become architects of spacetime itself. The foundation of spacetime engineering lies in Einstein's field equations, which describe the relationship between matter, energy, and the curvature of spacetime. These equations tell us that energy and matter determine the geometry of spacetime, while the geometry of spacetime determines how matter and energy move. It's a beautiful, reciprocal relationship. Matter tells spacetime how to curve, and curved spacetime tells matter how to move. For most of the century since Einstein first wrote down these equations, they remained primarily tools for understanding the natural world. We used them to predict the behavior of stars and galaxies, to understand black holes and gravitational waves, and to trace the expansion of the universe itself. But implicit in these equations is a more provocative possibility. If we could control the distribution of matter and energy with sufficient precision, we could potentially sculpt spacetime into whatever shape we desired. The energy requirements for such spacetime engineering are staggering by current standards. To create significant curvature in spacetime, the kind that might allow for practical time travel, would require energy densities comparable to those found in the cores of stars, or in the exotic matter that might exist inside black holes. We would need to manipulate not just enormous amounts of energy, but exotic forms of matter that may not exist naturally in our universe. One of the most studied concepts in spacetime engineering is the Alcubierre drive, proposed by physicist Miguel Alcubierre in 1994. This theoretical propulsion system would work by contracting spacetime in front of a spacecraft, while expanding it behind, creating a warp bubble that could carry the spacecraft faster than light without violating special relativity. The spacecraft itself would never move faster than light through local spacetime, but the space around it would be compressed and expanded in such a way that enormous distances could be traversed in short periods of time. From a time travel perspective, the Alcubierre drive offers fascinating possibilities. Because the spacecraft would be traveling faster than light relative to distant observers, relativistic effects would cause time dilation on a grand scale. A journey that took weeks or months from the perspective of the spacecraft crew might correspond to years or decades passing in the outside universe. The crew would effectively travel into the future during their journey, but the Alcubierre drive would require exotic matter with negative energy density to function, a form of matter that creates gravitational repulsion rather than attraction. While quantum field theory suggests that such exotic matter might exist in microscopic quantities, scaling it up to macroscopic levels would present enormous technical challenges. The energy requirements would be astronomical, possibly requiring the conversion of entire planets' worth of matter into exotic forms. Even more speculative are proposals for engineering wormholes, hypothetical tunnels through spacetime that could connect distant regions of the universe, or even different points in time. A traversable wormhole would require not only exotic matter to keep it open, but also incredibly precise control over the spacetime geometry at both ends. Creating a stable wormhole would be like threading a needle with cosmic forces, requiring technologies that can manipulate the fundamental structure of reality itself. The theoretical physicist Kip Thorne has studied the requirements for creating time machine wormholes in detail. His calculations suggest that such a project would require not just exotic matter, but the ability to manipulate that matter with precision across cosmic distances. One end of the wormhole would need to be accelerated to near light speed and then returned, creating a time difference between the two ends through relativistic effects. The engineering challenges would be comparable to reshaping entire regions of spacetime. Another approach to spacetime engineering involves cosmic strings, hypothetical one-dimensional defects in spacetime that might have formed during the early universe. These cosmic strings would be incredibly thin, but immensely massive, creating intense gravitational fields that could dramatically warp spacetime. If cosmic strings exist, and if we could somehow manipulate them, they might serve as tools for creating closed time-like curves or other exotic spacetime geometries. The energy scales involved in cosmic string manipulation would dwarf anything we can currently imagine. A cosmic string would contain the mass energy of entire galaxies, compressed into structures thinner than atomic nuclei. Moving such objects, if it were possible at all, would require the coordinated effort of multiple civilizations across vast regions of space and time. Some physicists have explored the possibility of using rotating massive objects to create closed time-like curves through a phenomenon called frame dragging. When a massive object rotates, it drags spacetime along with it, creating a swirling pattern in the fabric of reality. In principle, if you could create a sufficiently massive rotating object, perhaps a cylinder of ultradense matter extending for enormous distances, the frame dragging effect might be strong enough to create paths through spacetime that loop back in time. The construction of such a rotating massive object would represent an engineering project of unimaginable scope. You would need to gather matter equivalent to many stellar masses and arrange it in a precise configuration while maintaining rotation speeds that approach the limits of what spacetime itself can support. The precision required would be comparable to balancing a pencil on its point while riding a roller coaster, except the pencil would be made of neutron star material, and the roller coaster would be a trajectory through curved spacetime. Even if we could somehow overcome these technical challenges, spacetime engineering would raise profound questions about the responsibility that comes with such power. The ability to manipulate time itself would represent perhaps the ultimate technology, one that could reshape history, alter causality, and fundamentally change the nature of existence. The ethical implications would be as vast as the energy requirements. Consider the butterfly effect, the idea that small changes in complex systems can lead to dramatically different outcomes. If spacetime engineering made time travel possible, even tiny alterations to the past could potentially cascade into enormous changes in the present. A civilization with time travel technology would need to grapple with questions of temporal responsibility that have no precedent in human experience. There's also the question of temporal ecology, the idea that the timeline itself might be a kind of ecosystem that could be damaged by too much interference, just as biological ecosystems can be disrupted by the introduction of invasive species or the removal of keystone species. The temporal ecosystem might be vulnerable to the kinds of large-scale changes that spacetime engineering could make possible. Some theoretical frameworks suggest that spacetime itself might have natural healing mechanisms, ways of preserving causal consistency even in the face of potential paradoxes. These mechanisms might work like an immune system, detecting and correcting temporal inconsistencies before they can propagate and cause larger problems. But just as biological immune systems can be overwhelmed by sufficiently severe challenges, the temporal immune system might have limits that could be exceeded by advanced spacetime engineering. The study of spacetime engineering also leads us to contemplate the possibility of temporal archaeology, using time travel technology to directly observe historical events rather than inferring them from surviving evidence. Imagine being able to witness the formation of the solar system, the extinction of the dinosaurs, or the emergence of life on Earth. Such direct observation could revolutionize our understanding of natural history and answer countless questions that may never be resolved through conventional scientific methods. But temporal archaeology would come with its own set of challenges and ethical considerations. The act of observation itself might influence the events being observed, creating subtle changes that propagate forward through time. Even the gravitational influence of a time-traveling spacecraft might be enough to alter the trajectory of a crucial asteroid or the outcome of a critical evolutionary event. As we contemplate these possibilities, we begin to see that spacetime engineering represents more than just an exotic application of physics. It's a window into questions about the nature of time, causality, and our place in the cosmic order. The technologies required might be beyond our current capabilities by orders of magnitude, but the theoretical frameworks that describe them are helping us understand the fundamental structure of reality itself. Perhaps the most beautiful aspect of spacetime engineering is how it connects the largest scales of cosmic architecture with the most intimate aspects of temporal experience. The same equations that describe the curvature of spacetime around galaxies also govern the subtle time dilation effects that we experience in our daily lives. The exotic matter that might one day power wormhole generators is related to the quantum vacuum fluctuations that create virtual particles in empty space. In studying these possibilities, we're not just imagining fantastic technologies. We're exploring the deep mathematical poetry that underlies the structure of spacetime itself. Every equation tells a story about how matter and energy dance with space and time, and every theoretical possibility reveals new connections between the quantum realm and the cosmic scale. In the quiet moments between heartbeats, in the pause between one breath and the next, time flows forward with an inevitability that seems as fundamental as existence itself. We remember the past, but not the future. Eggs break but don't spontaneously reassemble. Heat flows from warm objects to cool ones, never the reverse. This directional quality of time, the fact that it has an arrow pointing from past to future, is so deeply embedded in our experience that we rarely question why it should be so. Yet when we examine the fundamental laws of physics, we discover something puzzling. Most of these laws are time-symmetric, meaning they work equally well whether time runs forward or backward. The equations that describe the motion of planets, the behavior of electromagnetic fields, and even the quantum mechanical evolution of particles make no fundamental distinction between past and future. If you were to watch a film of these processes running backward, the reversed version would obey the same physical laws as the original. This creates what physicists call the arrow of time problem. If the fundamental laws of physics don't distinguish between past and future, why does our everyday experience so clearly distinguish between them? Why does time seem to have a preferred direction, flowing always from past to future like a river that never reverses its course? The answer lies in a concept that bridges the gap between the microscopic world of individual particles and the macroscopic world of our everyday experience: entropy. Entropy is often described as a measure of disorder, but it's more precisely understood as a measure of the number of different microscopic arrangements that correspond to the same macroscopic state. A neat stack of papers has low entropy because there are relatively few ways to arrange the papers to maintain that neat appearance. A scattered pile of papers has high entropy because there are countless ways to arrange the papers while still maintaining the overall appearance of disorder. The second law of thermodynamics states that in any isolated system, entropy tends to increase over time. This law provides time with its arrow. The direction of increasing entropy defines the direction from past to future. But this raises another puzzle. If the fundamental laws of physics are time-symmetric, why should entropy preferentially increase rather than decrease? The resolution lies in the concept of statistical probability and the initial conditions of our universe. While it's theoretically possible for entropy to decrease, for scattered papers to spontaneously arrange themselves into a neat stack, such events become exponentially less likely as the number of particles involved increases. In a system containing billions of particles, the probability of a significant spontaneous decrease in entropy becomes so vanishingly small that we never observe it in practice. Our universe appears to have begun in a state of extraordinarily low entropy. The early universe was remarkably smooth and uniform, with matter and energy distributed in highly ordered configurations. As the universe evolved, this initial order gradually gave way to increasing complexity and disorder, driving the arrow of time that we experience today. This connection between entropy and time's arrow has profound implications for time travel. If we could somehow travel backward in time, we would be moving against the flow of entropy, swimming upstream against the river of increasing disorder. This might not be impossible in principle, but it would require enormous amounts of energy and precision to maintain coherent information while moving backward through time. Consider the challenge of traveling back to observe a historical event. As you move backward through time, you would be encountering light rays, sound waves, and other forms of information that are traveling forward through time. Your presence would disrupt these information flows, potentially scrambling the very evidence of the events you're trying to observe. It would be like trying to read a book while the letters are flying off the pages and rearranging themselves. The arrow of time also raises questions about the nature of memory and consciousness. Our ability to remember the past, but not the future, appears to be intimately connected to the thermodynamic arrow of time. Memory formation is a process that increases entropy. It requires energy to encode information in neural networks, and this energy eventually dissipates as heat. If time could run backward, would our memories run backward as well? Would we remember the future and forget the past? Some physicists have speculated about regions of spacetime where the thermodynamic arrow of time might point in different directions. In the far future, as the universe continues to expand and cool, the familiar sources of entropy increase might be exhausted. Stars will burn out, black holes will evaporate through Hawking radiation, and the universe might enter a state of maximum entropy where no further change is possible. In such a universe, would time still have an arrow, or would it become a static, directionless dimension? There's also the possibility of cosmological scenarios where time itself branches or merges. Some theories of quantum gravity suggest that spacetime might have a foam-like structure at the smallest scales, with multiple temporal dimensions braiding together in complex patterns. In such scenarios, the arrow of time might not be universal, but might vary from one region of spacetime to another. The relationship between entropy and time also connects to some of the deepest questions in physics about the nature of information. Black holes appear to destroy information when they evaporate, seeming to violate fundamental principles of quantum mechanics. This black hole information paradox has led physicists to reconsider the relationship between information, entropy, and time in ways that might eventually resolve questions about time travel and causality. One intriguing possibility is that information might be more fundamental than either matter or energy, that the universe is ultimately made of information, with matter, energy, space, and time all emerging as different aspects of more basic informational processes. In such a view, time travel might be understood as the rearrangement of information, rather than the movement of objects through a pre-existing temporal dimension. The arrow of time also plays a crucial role in our understanding of quantum mechanics and measurement. The process of quantum measurement appears to be irreversible once a quantum system interacts with a measurement apparatus. The superposition of possible states collapses into a definite outcome. This irreversibility might be connected to the thermodynamic arrow of time, with quantum measurement being fundamentally a process that increases entropy. If time travel were possible, it might allow us to observe quantum systems before their wave functions collapsed, potentially gaining access to information about quantum superpositions that would normally be destroyed by the measurement process. This could provide new insights into the foundations of quantum mechanics and the relationship between quantum mechanics and general relativity. As we drift deeper into these contemplations, we begin to see that the arrow of time is not just a curious feature of physics, but a fundamental aspect of the structure of reality. It connects the quantum realm to the cosmic scale, links the behavior of individual particles to the evolution of the entire universe, and bridges the gap between objective physical processes and subjective conscious experience. The river of entropy that carries us from past to future is not just a metaphor. It's a description of the deep current that runs through all of existence, giving meaning to concepts like cause and effect, memory and anticipation, birth and death. To travel against this current would require not just exotic technology, but a fundamental rewriting of the relationship between information, energy, and time itself. In the gentle flow of entropy's river, we find both constraint and possibility. The arrow of time limits our ability to revisit the past, but it also enables the emergence of complexity, consciousness, and beauty. Without entropy's steady increase, there would be no growth, no learning, no evolution, just a static universe frozen in perfect, eternal order. The river that prevents us from swimming backward through time is the same river that allows stars to shine, life to evolve, and consciousness to emerge from the quantum foam. As we near the end of our gentle journey through the physics of time travel, we arrive at perhaps the most mysterious territory of all, the relationship between consciousness and time. Here, at the intersection of physics and philosophy, neuroscience and metaphysics, we encounter questions that have puzzled humanity since the dawn of self-awareness. How does consciousness create our experience of time? Why do we perceive a flowing, now, when the equations of physics suggest that all moments are equally real? And what would it mean for consciousness to travel through time? The experience of time that each of us carries within our awareness seems fundamentally different from the time described by physics. Physics tells us about space-time as a four-dimensional block, where past, present, and future all exist simultaneously. But consciousness seems to carve out a special moment called now, and move through time like a spotlight, illuminating different scenes in sequence. This disconnect between the objective time of physics and the subjective time of experience has led philosophers to speak of the hard problem of time consciousness. When you remember yesterday's sunrise or anticipate tomorrow's rain, where do these experiences exist in the four-dimensional block of spacetime? Your memory of the sunrise is happening now, in your present moment, even though it refers to events that occurred in your past. Your anticipation of tomorrow's rain is also happening now, even though it refers to events that may occur in your future. This suggests that consciousness has a unique relationship with time. It can somehow transcend the sequential order of events and bring past and future into the present moment of awareness. The neuroscience of time perception reveals that our brains construct our experience of time through complex processes that integrate information from multiple sources. Different neural networks handle different aspects of temporal experience. Some track the passage of seconds and minutes. Others maintain our sense of narrative continuity across years and decades. When these systems are damaged by injury or disease, the result can be profound disruptions in time perception. Some patients lose the ability to form new memories, becoming trapped in an eternal present. Others experience time dilation or compression, where minutes feel like hours or hours pass in what seems like minutes. These neurological studies suggest that our normal experience of time is a construction, a model that our brains create to help us navigate through the four-dimensional landscape of space-time. This constructed nature of temporal experience raises intriguing questions about time travel. If consciousness creates its own experience of time, what would happen to that experience during time travel? Would a time traveler's consciousness need to be reconstructed to match their new temporal location? Consider the challenge of maintaining personal identity during time travel. Your sense of self is intimately connected to your memories, which form a continuous narrative stretching from your earliest recollections to your present moment. If you traveled backward in time, would your memories of the future still exist? Would you remember events that, from your new temporal perspective, haven't happened yet? Or would your consciousness somehow adjust to maintain consistency with your new position in time? The relationship between consciousness and quantum mechanics adds another layer of mystery to these questions. Some interpretations of quantum mechanics suggest that conscious observation plays a fundamental role in determining which possibilities become actual. The act of measurement causes quantum wave functions to collapse from suppositions of possibilities into definite outcomes. If consciousness can influence the quantum world in this way, might it also be able to influence the flow of time itself? This possibility becomes even more intriguing when we consider quantum entanglement and its relationship to consciousness. Some researchers have speculated that consciousness might operate through quantum processes in the brain, with quantum entanglement potentially connecting different regions of neural tissue or even different moments in time. If consciousness is indeed a quantum phenomenon, it might have access to non-local correlations that transcend ordinary spatial and temporal boundaries. The study of altered states of consciousness provides additional insights into the relationship between awareness and time. During deep meditation, psychedelic experiences, or certain types of brain stimulation, people often report profound changes in their perception of time. Some describe experiencing all moments simultaneously, feeling a sense of eternal now that encompasses past, present, and future. Others report traveling through time, visiting memories with a vividness that makes them feel present in past events. These altered states suggest that our ordinary sequential experience of time might be just one possible mode of temporal consciousness. Perhaps consciousness is naturally capable of experiencing time in multiple ways, but our normal waking state constrains this experience into the linear flow that helps us function in daily life. Time travel might not require exotic physics, but rather a different mode of consciousness, one that can navigate through the four-dimensional landscape of spacetime with the same freedom that ordinary consciousness navigates through space. The concept of eternal consciousness that appears in various spiritual and philosophical traditions offers another perspective on time and awareness. According to these views, consciousness itself exists outside of time, experiencing all moments simultaneously from a transcendent perspective. Individual human consciousness might be like a focused beam of this eternal awareness, illuminating different moments in sequence, but ultimately connected to a timeless source of experience. From this perspective, time travel might not involve moving consciousness through time, but rather expanding consciousness to encompass multiple temporal locations simultaneously. A time traveler might not be someone who moves from one moment to another, but someone who becomes aware of their presence at multiple moments at once, like a person suddenly realizing they can see in all directions simultaneously. The relationship between consciousness and free will adds yet another dimension to questions about time travel. If the future already exists in the four-dimensional block universe, are our choices predetermined? Or does consciousness somehow create the future through the act of choosing, bringing certain possibilities into existence while leaving others unrealized? If time travel were possible, would it reveal a predetermined future? Or would the time traveler's consciousness participate in creating the reality they observe? Some theories suggest that consciousness might work like a quantum measurement device, constantly collapsing possibilities into actualities through the process of experience. Each moment of awareness might select one path from the quantum multiverse of possibilities, creating a unique timeline that reflects the choices and observations of conscious beings. In this view, time travel would not be passive observation, but active creation. The time traveler's consciousness would participate in determining which version of the past or future becomes real. The mystery of consciousness also raises questions about the continuity of experience during time travel. If you traveled 1 year into the future, would you experience the intervening year as a gap in consciousness, like dreamless sleep? Or would your consciousness somehow traverse every moment of that year, experiencing a full year of subjective time even though you arrived at your destination instantly from an external perspective? These questions become even more complex when we consider the possibility of encountering your own consciousness at different points in time. If you traveled back to observe your younger self, would you be encountering the same consciousness at a different stage of development? Or would there be two separate streams of consciousness existing simultaneously? The very notion of personal identity becomes fluid when consciousness can potentially exist at multiple points in time. Perhaps the deepest mystery is how consciousness creates the experience of now, the sense that there is a special moment that is uniquely present and real. Physics offers no explanation for why any particular moment should feel more real than any other. Yet this feeling of nowness is perhaps the most fundamental aspect of conscious experience. Understanding how consciousness creates nowness might be the key to understanding how it could navigate through time. As we contemplate these mysteries in the quiet space of approaching sleep, we might find that the relationship between consciousness and time touches something profound within our own experience. Each night, as we drift from waking consciousness into dream, and then into the timeless realm of deep sleep, we experience a kind of time travel. We lose our connection to the sequential flow of time and enter states where past, present, and future can blend together in ways that defy ordinary logic. Perhaps dreams offer us a glimpse of what consciousness might be like if freed from the constraints of linear time. In dreams, we can visit childhood memories, anticipate future events, and experience impossible scenarios where different temporal threads weave together in seamless narratives. The dream state might be consciousness's natural mode of time travel, showing us possibilities that exist beyond the boundaries of waking experience. As our exploration of time travel draws to its gentle close, we find ourselves standing at the edge of a vast ocean of possibility, where the waves of past and future meet in the eternal moment of now. We've journeyed through the curved corridors of spacetime, danced with quantum possibilities, and contemplated the deepest mysteries of consciousness and time. What emerges from this exploration is not a definitive answer about whether time travel is possible, but rather a profound appreciation for the beautiful complexity of the universe we inhabit. The physics of time travel reveals that we live in a cosmos far stranger and more wonderful than our everyday experience suggests. Time is not the rigid framework that common sense would have us believe, but rather a fluid dimension that bends and flows in response to matter, energy, and motion. The universe permits time dilation, allows for the possibility of closed time-like curves, and may even contain microscopic wormholes that connect distant moments across the fabric of spacetime. Yet each of these possibilities comes with its own profound challenges and mysteries. The energy requirements for practical time travel exceed anything we can currently imagine. The paradoxes that seem to arise from backward time travel force us to reconsider our most basic assumptions about causality and free will. The relationship between consciousness and time remains one of the deepest puzzles in all of science, connecting physics to philosophy in ways that challenge both disciplines. Perhaps the most beautiful lesson from our exploration is that the question of time travel cannot be separated from broader questions about the nature of reality itself. To understand whether time travel is possible, we must understand the relationship between space and time, matter and energy, quantum mechanics and gravity, consciousness and cosmos. Time travel serves as a lens through which we can examine the fundamental structure of existence, revealing connections and mysteries that might otherwise remain hidden. The theoretical frameworks we've explored, from Einstein's relativity to quantum mechanics to theories of consciousness, each offer their own perspective on the nature of time and the possibility of traveling through it. Relativity shows us that time is malleable, that it can stretch and compress in response to motion and gravity. Quantum mechanics reveals that the microscopic world operates according to principles that seem to transcend ordinary notions of causality and sequence. The study of consciousness suggests that our experience of time may be more fluid and creative than we typically realize. These different perspectives don't necessarily contradict each other, but they do reveal that time is a phenomenon of extraordinary richness and complexity, like a multifaceted crystal that shows different colors depending on the angle from which you view it. Time reveals different aspects of its nature, depending on the theoretical framework through which you examine it. The practical challenges of time travel, the exotic matter requirements, the energy scales involved, the technological precision needed, may place such technologies far beyond our current capabilities. But the theoretical possibility remains, embedded in the mathematical structures that describe our universe. Even if we never build a time machine, the fact that the laws of physics seem to permit such devices tells us something profound about the nature of reality. The paradoxes and puzzles that arise from contemplating time travel serve their own important purpose. They force us to think carefully about causality, logic, and the nature of existence. They reveal assumptions we didn't know we were making and open up new ways of thinking about familiar concepts. In wrestling with the grandfather paradox or the information paradox of black holes, we're not just solving puzzles, we're exploring the logical structure of reality itself. As we consider the future of time travel research, we can see several promising directions. Advances in our understanding of quantum gravity might reveal new connections between the quantum world and the large-scale structure of spacetime. Developments in neuroscience and the study of consciousness might illuminate the relationship between subjective temporal experience and objective physical time. Improvements in our ability to manipulate matter and energy at extreme scales might eventually make some forms of spacetime engineering feasible. But perhaps the most valuable insights from studying time travel come not from any particular technological possibility, but from the broader perspective it offers on existence itself. Time travel research reminds us that we live in a universe of extraordinary depth and mystery, where the familiar concepts of everyday life, time, space, causality, consciousness, turn out to be far more subtle and complex than we might expect. In contemplating the possibility of journeying to other times, we're also contemplating the nature of our own temporal existence. We're reminded that our lives unfold within the vast four-dimensional landscape of spacetime, where every moment we've ever experienced continues to exist in the eternal block universe of physics. We're encouraged to think about the relationship between memory and reality, between anticipation and actuality, between the flowing experience of consciousness and the static mathematics of physical law. The study of time travel also connects us to the deepest questions about human nature and cosmic purpose. If time travel were possible, what would it mean for concepts like growth, learning, and moral responsibility? How would the ability to revisit the past or glimpse the future change our understanding of choice and consequence? These questions don't have easy answers, but they point toward the profound ways that scientific discoveries can reshape our understanding of what it means to be human. As we drift toward the conclusion of our journey, we might reflect on the fact that we are all time travelers of a sort. We're constantly moving through time at the rate of 1 second per second, carrying our memories of the past and our anticipations of the future through the flowing moment of now. The consciousness that allows us to experience this temporal journey is itself one of the deepest mysteries in the universe, somehow binding together past, present, and future into the seamless experience of a life lived through time. The physics of time travel reveals that the universe is far more flexible and mysterious than our everyday experience suggests. But it also reveals that we are already participants in the deepest mysteries of existence. The same quantum processes that might one day enable exotic forms of time travel are already at work in our brains, creating the neural correlates of consciousness. The same relativistic effects that could power time machines are already subtly affecting our daily lives. From the GPS satellites that guide our navigation to the cosmic rays that shower down from space. In the end, the question of whether time travel is possible may be less important than what asking that question teaches us about the nature of reality, consciousness, and our place in the cosmic order. The journey through the physics of time travel is ultimately a journey toward a deeper appreciation of the magnificent mystery of existence itself. A mystery that encompasses not just the possibility of traveling through time, but the miracle of consciousness that allows us to experience time at all. As we settle into the quiet comfort of approaching sleep, we might find peace in knowing that we're part of this vast cosmic story, where consciousness and cosmos dance together through the dimensions of space and time. Whether or not we ever build time machines, we're already traveling through time together, sharing in the ancient journey of matter becoming aware of itself, of the universe coming to know its own magnificent complexity through the experience of conscious beings like ourselves. In the gentle flow of breath and the quiet rhythm of the heart, in the soft transition from waking to dreaming, we find our own natural form of time travel, a daily journey into altered states of consciousness, where the normal rules of sequential time dissolve into the timeless realm of dreams and rest. Perhaps this is time travel enough. The ability to visit the past through memory, anticipate the future through imagination, and find peace in the eternal present moment, where consciousness meets cosmos in the quiet miracle of awareness itself. Sleep well, fellow time travelers. In your dreams tonight, you may find yourself visiting times and places that exist only in the infinite possibilities of consciousness, exploring the vast landscape of what was, what is, and what might yet come to be. Rest in the knowledge that you are part of the universe's ongoing exploration of its own nature, a living embodiment of the cosmos coming to understand itself through the beautiful mystery of conscious experience. Sweet dreams, and may your journey through the night be filled with wonder at the magnificent puzzle of existence we all share. Until we meet again in the flowing moment of tomorrow's now, travel well through the gentle currents of time, carried by the rhythm of breath and heartbeat toward whatever discoveries await in the endless dance of possibility that is our universe.